So let's move to continuous model. I fixed the problem of the placement of the slide. I hope it doesn't happen again. Okay, so we could just say have an example of difference equation for microorganisms growth. So we could just say that here I put n of t plus 1, but we could just say n plus 1, it's equal n, so the number of microorganisms that were before, plus the number of microorganisms that were born, okay? So consider the simple experiment of growing bacteria on a nutrient medium, and if you put them in favorable conditions, they will have a constant growth rate lambda over time. For n of t as the bacterial density at time t, the situation can be modeled using this equation. Okay. So I'm trying to go from this model to the continuous one. So we could just write this model like this. Or if instead of considering a change over 30 seconds or half a minute, because before the time change was 1 minute, and then we could just write like this. Or if we take into account some arbitrary time change h, then we could just write it like this. So for h going to 0, so we take the limit, then we would have the derivative of n, the function n of t. So our model could be just written like this. So the continuous model is when we choose to see the time change as infinitely in the, like, really small, yeah. Okay, so this is our first differential equation. So we could just write this model for the bacterial growth on a nutrient medium in this shape. So this equation was first studied by Malthus to model population growth. So a question is, what does it mean to say we got a solution for this equation? And how can we find this solution? But before, I would like just say something. So at this model here, we have as hypothesis that the bacteria has enough nutrient in the medium, so it never ends. So it means that the population will grow exponentially. So yeah, if we take into account that there is not enough nutrient, we should use the logistic equation. I think I'm going to show some example about this. So the question, what does it mean to say that we got a solution for this equation? So here we are trying to find a function n that satisfy this relation, that del n del t, it's equal lambda n. Okay, so finding the solution means to say that we found this function that satisfies this relation. So let's find the solution of this equation like this. So we had that dn dt, it's equal lambda n. Then I just kind of dividing by n and letting the lambda dt on the other side. And then I'm integrating it on both sides, and then here. And then I, because it's not not defined integral, so I need to add this constant here. So on the left side I get ln of n, and the right side I get lambda t, because here I'm integrating on t, here integrating on n. So I get that the solution of this equation is something like this. So here I just say that okay, so I just say that n0 it's equal e c0. Okay, so yeah, so we still would need to find n0, which is a constant that's determined by the initial conditions. So if we're saying that the solution of this equation is this, it means that if we substitute this n function here, it would be satisfied. So it would on what's on the left side would be equal what's on the right side. So then I just simulated the solution for lambda equal 1, and then I choose different initial conditions, so which is related to n0, and then I get this behavior here. Yeah, so then I just put some direction fields, which is just the plot of n versus the dn dt, because dn dt is the slope of the tangent line on a curve, right? So then I just plot these slopes, and we can see by this direction field plot that 0, so we have that original equations like n. I'm not talking about steady state yet, right? Okay, so but just to have add some intuition here. So n of t is equal right. Yeah, okay, and I choose lambda equal 1. So we can see that 0 is some steady state, but some unstable steady state, because if you start your if you start with initial condition 0, your solution will be constant over it won't change, right? But if you go a little bit away from this point, it just run away. So it's some unstable steady state. And like, as I said, the solution of this equation will just grow exponentially. So it means that the population will grow really big. So it could even be infinite at some point, so tend to infinite, right? And if we want to include at this model some realistic thing, so that at some point the microorganism, if you don't put nutrient and you don't add space, at some point they just will grow, and then they will just repopulate all that space, and they won't have enough nutrients. Then there are some possible models. So you can use Verhulst. We already said this. So this is the logistic equation, and there is also the Gompertz. And then I just simulated the Verhulst model with parameters lambda equal 1 and k equal 2. And we have the following directions field graph. So we can see here that 0 looks like to be some steady state, unstable, because if you go a little bit away from it, so here is time. Yeah. So sorry, in this plot actually it's t over n of t, and then at each point here I put the tangent, okay, the slope of the tangent line. So here again, so 0 is some steady state, but looks like it's unstable, and 2 looks like another steady state, but it looks like that is stable, because if you start away from this point, the solution will tend to y to n equal 2. Yeah. Okay. Another thing that I want to mention. Yeah. So here in this case we have a nonlinear equation, and in the Malthus model, the dt, so it is some linear. Okay, so we can find the solution explicitly, but in the nonlinear case it's not possible, or at least it's not so easy. Okay, so the solution, that's what I wanted to say. So the solution for the logistic equation of Verhulst equation is more difficult to be obtained analytically, since it's nonlinear. We can have an idea of the behavior studying the steady state and its stability. So by the direction field, we see two steady states, n equals 0 and n equal 2, and the first one is unstable and the other one is stable. I'm going to make some review about ODE and PDE. I started with ODE. I'm going to define it and show how to find its solution for some linear cases.